The extra time in the schedule. Okay. All right. So next up we have Jeannie Kleinhenz. Did I get that right?
Yeah.
Okay, good. All right. And she's going to speak about characterization of volatiles loss from soil samples at lunar environments. Okay.
All right. All kinds of toys. Okay. So I'm from the NASA Glenn Research Center. I'm going to be talking to you again about the Resource Prospector mission. So this is some characterization work we've been doing to characterize volatile loss at lunar environmental conditions. So you've seen this slide a couple times today. I'm not going to spend too much time for it, but again, RP, or Resource Prospector, the mission is to ground truth the water that was detected at the lunar polar regions. So to characterize the nature and distribution of the volatiles in the subsurface, we've got a drill mounted on a rover with a processing and analysis system, which you heard about this morning from Janine. A prospecting unit, you heard about that, I think, this afternoon, later this morning from Ted. And then there is a presentation or a poster session on the drill by Chris Sackney. So I encourage you to look at all the different components involved here. But what I'm going to be talking about is the integrated thermal vacuum test program that we've been running. So the goal here is to do a series of ground-based dirty thermal vacuum tests to better understand the subsurface sampling operations for RP. This includes looking at volatile loss during the sampling operations, looking at hardware performance overall and improving the hardware based on that, and also looking at the overall concept of operations for the mission scenario. So we've done a total of 5 test campaigns over the course of 5 years, each year with slightly advancing hardware and added hardware. So we're up to 3 RP subsystems right now that we've tested together. We've done volatile sampling for 4 of those years, so the first year was just kind of hardware tests. So the overall goal of the program is to use flight-forward Regulus sampling hardware and empirically determine volatiles retention at lunar relevant conditions. So this data feeds into theoretical predictions, our numerical models. We're also trying to determine the driving variables for water retention and to bound the water loss potential that there might be to define measurement uncertainties for the actual mission. So this talk, I only had 15 minutes, so I'm kind of giving you a brief overview here. I want to spend a little bit of time talking about the facility we use, and then I'm going to kind of summarize what we've been doing and give you a very brief overview of some of the results we're seeing. So this is our facility at the Glenn Research Center. It's the Planetary Surface Simulation Facility. It's also called VF13. VF is just vacuum facility, number 13. And you can see it in the picture here. It's 3.6 meters tall, 1.5 meters in diameter. So this is ideal for drill testing because we can have a meter drill and a meter of sample or soil to drill into. You can see the fixed base here of the chamber. The soil bin is in the center, and then we load it up with the cap and the cold wall. So it's got a cold wall cooled by liquid nitrogen. So this lets us chill in the hardware to temperatures between atmospheric and liquid nitrogen temperatures. And then it's got a separate liquid nitrogen source, which we wrap around the soil bin so we can cool the soil down to those temperatures as well. We can achieve pressures on the order of the -6 scale torr with soil in the chamber. So this is lunar relevant, not quite as low as real lunar conditions. And just a little plug, not related to RP, we're currently upgrading with a Mars gas capability. We've got a brand new mass spectrometer on there, and it's going to control a flow panel so we can actually maintain Mars gas composition in the chamber while we're performing things like ISRU tests. For RP, we're using this cylindrical soil bin, 1.2 meters tall. It holds about 100 kilograms of simulant. We're using LHT simulant for these tests. It's got a clamp-on cold shell to chill it in. So you can see this is our old. We had some coolant loops. This year we upgraded. It's a concentric shell, so we're fully filling LN2 around the outside of the tube. We've gotten as low as -160 degrees C in the soil. Also available for use, we do have a square bin. It's a meter cubed, so it can hold 800 kilograms of simulant. It's not chilled, but this is available for other types of testing. And then all the hardware in the chamber, that's the drilling hardware and the like, can be mounted to a robotic translator so that we can access various points in the chamber so that we can make use of one pump down and get multiple drill holes. We've been able to do, I think, 4 to as many as 6 in the past holes per test with one soil bin. The soil bin test prep, so we're doping the soil with water to mimic lunar polar conditions. You can see some of my preparation equipment in the lab here. I can add water, mix it uniformly, and then I compact the soil to get some reasonable densities in there. There's no way to measure soil moisture in situ during the vacuum process. So what I do is I get a reading on it before test and then after test. So these so-called post-mortems, you can see here from like all the different tests we've done. Moisture content is plotted versus depth from the surface. What I want to point out here is that if you look at the depth above about 20 to 30 centimeters, the moisture content is relatively uniform. So the desiccation due to vacuum exposure is restricted to the top 20 to 30 centimeters. So all the sampling operations we do for RP, we do beneath that. So this shows the hardware in the chamber. The start items are the actual RP hardware we're using. So we're using the drill in its current condition, the Nervous, and this year was the first time we incorporated the oven unit in the system. So you can see them here. This is the fixed base of the chamber, everything stacked on top. You can see the drill on top, the yellow. This is our robotic translator here, so everything's mounted to that. The soil bin's kind of hidden back in here, but it's mounted in the base. And then this is looking down. Here's the drill, the soil surface here, Nervous, which you saw this morning. And then this is the oven module here. In place of the oven, we typically use specially designed sample capture mechanisms. These allow us the benefit of getting more than one sample per test. And those are shown here. So what happens is the drill samples, so the bottom 10 centimeters of the drill are specially designed flutes that the sample is captured on. So you bite in 10 centimeter bites. So you go down, pull up a sample, brush that off, go down, pull up another one, and so on. When we want to capture one of those samples, we brush directly into a crucible here, and you can see them real here. Brush into the crucible, seal at vacuum conditions. We can get 5 of those samples per test. And then after we're done and we vent up, I take those samples into the lab and bake them out using ASTM standard methods. That's how we determine the moisture content of the samples. So this is a list of all the variables we've used over the course of the years. So some of them are tightly controlled, some of them we do our best. Pressure, we go as low as possible. Anymore, our test pressures are about 3 to the -6 scale, 3 to the -6 torr, somewhere in there. Early tests, we were in the -5s. We've done much better now. The shroud temperature of the cold wall, we can control that. Most of the tests we run, we do at -50 degrees C. The idea there is to mimic a sunlit kind of temperature. The soil bin temperature, we go as low as possible. We want to get that soil as cold as possible. Our target is at least -100 degrees C. It actually depends on the soil moisture content for how cold we can get, and to some extent the time we let it cool. The soil bin moisture content, the highest we test with is 5 weight %. That's based on the L-Cross results. We've done some lower than that, and we've also stratified the bin where we've had wet and dry layers mixed in, separated by a thin foil barrier. The sample crucible temperature we're depositing into, we typically keep that as cold as possible. We did heat that in a couple tests to play with some con-op scenarios. The sample exposure time, so it typically takes 5 minutes for us to brush off the sample into the crucible. There were some times we delayed that purposely, again, to play with con-op scenarios and see how that affected things. And finally, the sample size. We're targeting 10, 15 grams. Our maximum is 20. We do get a range, so that somewhat impacts the results as well. Okay, this is a sample of the results. So to go through this real quick, at the bottom here, let's start here, is drill. This is just from a sampling bite. So what you're seeing here is the black line is the drill position. So we're drilling down. When we're at the peak here, we're at depth. Here's where we're retracting the drill. And then this gray region here is when we're brushing into the sample, when we're capturing the sample into the crucible. The red is the drill bit temperature. The thing I want to point out here is that we have a RGA, a residual gas analyzer, on the system running during the entire drilling operations. And the blue line in the center here is mass number 18, so there's water. And what I want to point out here is during the drilling and retraction, that water signal is pretty constant. As soon as we start brushing that material off the drill into the crucible, that's when we're seeing the water loss. Those are when we're seeing the peaks. This is consistent for every sample we take. We see these peaks. So here's kind of an overview of the results. Again, I'm giving you kind of a sample of some of the results we're seeing here. I'm plotting sample water loss as a percent versus the starting content, water content of the moisture, or of the soil bin. So what you can see, first of all, here is that for higher starting moisture contents, we have better water retention. So the drier the soil bin, the more loss we see. So that's a pretty clear trend here. The other thing I want to point out is the size of these symbols correlate with the size of the sample that we've recovered. So the smaller samples, we didn't get as much material into the crucible, and there's more scatter in the results. So we're just dealing with some error there. So this is kind of spinning that in a little different way. Again, I've got soil bin moisture content plotted at the bottom. This is mass loss rate. So this is basically the water lost in grams over the exposure time. So again, the size of the symbol correlates with the sample mass. And what I want to point out here is that for similar sample sizes, we're seeing a similar loss rate. So you can see the cluster down here of the smaller samples, and then up here, mass loss is pretty consistent for those. So the clear thing is, with the color representing the water retention, where blue is better water retention, so of course, if your mass loss is consistent, then if you've got more water to start with, you're going to retain more water overall as a percent. So really, we can take this mass loss number and correlate that to sublimation rate, right? So, but the open question is, what is the driving temperature for the sublimation? So over the course of our sampling procedures, we're exposed to at least 4 different temperatures. We've got the temperature of the soil bin to start. We've got the temperature of the drill bit. We've got the temperature of the environment, or that cold wall temperature, and then finally the temperature of the crucible. And those are all different. So to start to get an idea of what might be the driving temperature, this is that mass loss rate plotted against all of those. So this top corner is the cold wall temperature, or the environmental temperature. Soil temperature is here, drill bit temperature, and crucible temperature. So you can see this one and this one, there's no clear trend. So if I'm fishing for trends here, the 2 that I'm seeing are the drill bit temperature, where there's a slight trend with higher temperature of the drill bit corresponding to slightly higher mass loss rate. However, that's somewhat convoluted because it just so happens that the lower temperatures are also the smaller sample sizes, so we're a little convoluted there. But soil temperature does seem to be a clear trend, with the warmer soil temperatures corresponding to a higher mass loss rate, so there's a trend there. I'll note that there are 3 outliers here. Those are where we captured into the oven as opposed to the sample crucibles, so there is a difference in the technique there. So to date, we've conducted a total of 4 test campaigns with volatile sampling in our chamber. This totals 43 samples that we've taken, 43 soil samples. We've done 4 different moisture conditions for the soil. 26 of the samples were from the same moisture content, same soil prep. And that's that 5 weight % as predicted by L-Cross. So we do have some data there to compare. Thus far, we've done 3 RP subsystems, drill, nervous, and oven, tested them all together, so we're really moving toward an integrated test program here and getting some good results on how everything plays together. So again, this is a flight-forward approach. We're feeding this into theoretical predictions, we're adjusting con-ops as we're getting the data back, and we're starting to bound loss. And I'll put in a plug here, so I gave you a quick sample of the results we're seeing. The analysis is ongoing. I'm still working on it, but I do plan to have a summary paper at the ASCE Earth and Space Conference in April, so stay tuned for that if you want some more information. So, thank you very much.
So the grain size of the ice, I think, would be a really important parameter here. Basically, surface area of the ice that's exposed to the vacuum would drive your sublimation rate. It's sort of hard to know how well it could be controlled. You might have smaller grain sizes with less water content, or I'm not sure. Is there anything you did to try and control that?
Yeah, so
measure it.
That's tricky without adding water as you're freezing. So what I do is I dope the soil in the lab and get as uniform mixture as possible and then freeze it in place during vacuum exposure. So we really can't control that in the current scenario.
Yeah, I mean, could you add the ice to the soil and mix it at temperature?
I don't have a means to do that right now,
okay.
is the answer. So the only way you could do that is if you somehow filtered it up through there and froze it as you're kind of adding it at vacuum conditions. That's very tricky.
Well, one thing that we've done is you use a spray and then you spray it into liquid nitrogen and mix it at liquid nitrogen temperatures and then bring it up. But we could talk about it later.
Yeah, and the trick too is I do have 100 kilograms of soil I'm dealing with here. So. Plus, I want to compact it to get the right density. So there's a lot to do at vacuum operations at that point. And as soon as you expose a very cold sample to the environment, you're adding moisture from the air. So, there's a lot of games to play there. So.